We're going on about what makes a planet habitable. We've covered a number of topics, getting the temperature right, getting the right chemical elements that support life. And you can listen to the two earlier segments. But right now, let's address two important topics. Is life only carbon-based? So we're aware of carbon as essential to our lives. It's the basis of amino acids and thus proteins. It's the basis of DNA and thus our genetics and all of our gene expression. It's the basis of lipids that allow us to, oh, John, take it off of autofocus if it's not. Oh, okay, yes, that's okay. Sorry, I was interrupted. We're also taking videos here. Anyway, lipids are important for segregating all the parts of the cell so that the chemical reactions get properly isolated from each other until needed. Now, some people have said, what about silicon? If you go to the periodic table of the chemical elements, then silicon is right below carbon. It's an analog. Can you make similar compounds with silicon? Well, let's take the simplest hydrocarbon, that's methane, CH4, a carbon bonded to 4 hydrogens. Can you make that with silicon? Yes, you get silane, SiH4. Let's go to the next step. You have to get long molecules. How about making a chain? The simplest chain, the saturated hydrocarbon ethane, C2H4. 2 carbons with a single bond between them, and the other 6 valences of carbon of the 2 carbons are satisfied with hydrogen. So CH3, CH3. Can you make that with silicon? Yeah, you can make disilane, Si2H6. Unfortunately, it catches fire spontaneously in the air, and so does every other analog of silicon. Silicon bonds are not nearly as stable as carbon bonds, partly because the silicon atom is fatter. It means they sit further apart from each other in any of these bonds, and that makes a weaker bond. So there's lots of good chemical evidence that says, no, silicon cannot be the basis. In fact, you can take any other element. Carbon is the only one that can bond to almost everything you can name. And that makes it very, very handy for life. Actually, I would say necessary. Now, what about water? People have said there's analogs of water. Let's consider something called isoelectronic compounds. That means they've got the same number of electrons on the elements in their outer shells that can form chemical bonds. So if you take oxygen, 6 electrons, hydrogen, 1 each. There are 8 electrons in those valence shells, okay? What is ammonia? Ammonia has 5 electrons on the nitrogen and then 3 on the 3 hydrogens, also 8. And then if you go down to carbon, that the analog there is methane. Okay, so what are these compounds like? They're all gaseous until you get to really, really low temperatures. Low temperatures also means really slow chemical reactions, and that doesn't work. Okay, there are some forms of life, perhaps in the deep rock, that do have a very slow lifestyle, but they're not going to be intelligent life, that's for sure, and they're not dominant by far. So water is very handy for being liquid and solid and vapor at a nice range of temperatures. In fact, we experience them all. We see water vapor in the air. We breathe water vapor. We see water vapor turning into clouds and raining out, liquid water. We see ice. And one of the reasons that it has much higher melting and boiling points is it creates among its own molecules these semi-weak bonds called hydrogen bonds. And those stabilize the liquid and the solid to very high temperatures by the standards of those other 2 compounds, methane and ammonia. All right. that also gives water some really cool properties that certainly work very well for earthbound organisms. So water is one of possibly the best solvent of all chemical compounds known. There's dimethylformamide as the best organic solvent, but you don't want to get that on your hands, among other things. Okay, so it's an extremely good solvent for lots of molecules, especially ionic compounds, salts, and so on. And those ionic compounds are great for messaging, like in our nerves with the sodium and potassium and other ions shuttling around. Also, water has a really high heat capacity. That means it takes a lot of energy per mass to move its temperature up a given amount, like a degree. It's about 4 times as much as other common chemicals. What does that mean? Well, it means that it takes a lot of energy to change the temperature of anything that has water in it, like oceans. That's a big moderator of temperature that keeps the Earth and our bodies from swinging up and down in temperature. Also, water has an extremely high dielectric constant, and that basically is the amount of shielding between charged particles in solution. So if you take something that is not as high in dielectric constant, you can't get many of these ions together close to each other. In water, you can. Another neat property of water is one we all know, that it floats and as ice. And that's really handy. Otherwise, life on Earth would probably be mostly in a little thin skin of melted water. Because if you were in our so-called temperate zone and you went through the winter, but ice sank, it would stay like permafrost in the soils of the north down at the bottom, and every year we might get a couple of meters of liquid water on the surface. That's not conducive to all kinds of life. Okay. Now, going back to the other one, ammonia. As I said, it's dicey for the low temperatures where it has the right liquid phase and so on. If you take the average of its melting point and boiling point, it's 55 degrees Celsius, about 100 degrees Fahrenheit, lower than what it is for water. That is not good for biochemical reactions. Another thing is the greenhouse effect. Okay, what happens if, take the Earth. The main greenhouse gas is water. That's not to say that carbon dioxide and methane and nitrous oxide and all those are unimportant. In fact, they are the drivers. They drag along the water. Water would do nothing without those guys. Without carbon dioxide, methane, and all those others, the Earth would be frozen. And there wouldn't be enough water vapor to bring us out of that frozen condition. When you got enough of those other gases, water melts, and it contributes to the greenhouse effect. That effect is 33 degrees Celsius rise, about 60 degrees Fahrenheit over what the Earth would be without the greenhouse effect. So the average temperature of the Earth viewed from space is what you'd see without the greenhouse effect. It's minus 18 degrees Celsius. And I'm so used to Celsius, I'd have to think what that is in Fahrenheit. I don't know, 0 Fahrenheit, roughly. But what is our actual temperature at the surface? It's plus 15 degrees Celsius, 59 degrees Fahrenheit. It also happens to be the average temperature at Las Cruces, so we're representative here. Okay. Now, if you wanted liquid ammonia around, its vapor pressure, that is, how much of it goes into the gaseous phase, would be really high. And that would give us a huge greenhouse effect. Okay, you get to the right temperature for biochemical reactions, even going the lower levels. You get enough ammonia gas in the atmosphere that it really heats up the surface, and that's a positive feedback. It gets hotter. There's even more. You get a runaway greenhouse effect. Ammonia would not work. So let's say we're going to count on carbon and we're going to count on water. Now, a little bit more. You have to adjust the greenhouse effect over time. Okay, the sun's output about 2.2 billion years ago was only about 70% of what it is now. But we stayed warm enough for liquid water and early life, the cyanobacteria especially, because we had a strong greenhouse effect. We had methane in gobs up in the atmosphere, much more powerful greenhouse gas. And then there was a time when life almost did itself in because it generated oxygen in photosynthesis. There's a big problem for what you might call electron acceptors in photosynthesis. Water is so abundant, you might say the cyanobacteria evolved to use it. You wouldn't say they figured it out because they don't have brains, but anyway, they did manage to evolve a way to use water, and they split that into hydrogen for reducing power and oxygen gas. Well, we like that now, but the rest of the world, even the cyanobacteria, really didn't, because what it did was oxidize the methane in the air to carbon dioxide. That's a much weaker greenhouse gas. So the earth got colder, and then as it got colder, it got ice. That reflects more of the energy away from the sun. It gets colder yet. It's a positive feedback. Well, the end result was snowball Earth, and it happened at least twice, that the Earth almost or completely froze over, which, that wouldn't be all the way down in the depths of the ocean. But it did get cold and almost did in everybody. Well, there were only bacteria then. All right. It's a good thing it didn't happen with higher organisms. So what brought us out of snowball Earth? Well, getting enough carbon dioxide in the air, really pumping it up. Volcanoes brought a lot of carbon dioxide up. Well, then there was another positive feedback so that the ice all melted and it got warmer and warmer. And the idea is that it might have hit 50 degrees Celsius as mean temperature, 122 Fahrenheit. And that almost cooked everybody. So I tend to dismiss this idea of Gaia, the goddess of the earth, or the hypothesis saying that life basically adjusts the planet to keep itself going. No, it almost did itself in. And we're going to get into a little bit more of that detail